So after limits, the next natural thing to talk about is the derivative. And how does the derivative work now that we have multiple variables? Before we do that, I just want to mention real quick the idea of continuity does not change with multiple variables. So that's why I'm not going to do like we won't have a whole video on it because it's really just a footnote here. So I'll just include it here. So continuity, the idea is the same, which is that a function is continuous at a point xy if, or rather at the point AB, I should say, if the limit as xy approaches AB of f of xy is equal to the output at that point. So f of AB. So same idea that we had in the single variable calculus applies here. So again, it would just be about finding that limit, taking that limit. At this point, after going through all of Math Tools 1 and 2 especially, or if you didn't do that, just, with prior experience working on calculus, you should have a pretty good intuitive sense about whether or not a function is continuous. A lot of the functions we're going to deal with anyway. So, we don't really need to rely on this definition too much. You kind of should know, when we have a denominator, there's going to be points of discontinuity, things like that, right? Logarithms, same idea. So we won't focus on that too much this time. So moving on to the partial derivatives then. So we know that with single variables, so using our trusty f of x equals x squared example, with single variables, we define this as the tangent line, the slope of the tangent line at a point, right? So if we have this point right here, say that that's 2, x equals 2, right? Then we would say that this is the slope of the tangent line at the point x equals 2, which on this graph would be the point 2, 4. So our derivative f prime of x would be equal to 2x, which remember this is equal, we would say that this is d dx of x squared is equal to 2x using that Leibniz notation, which will be pretty common here with the partial derivatives. So the slope of the tangent line at that point, then we just plug in x equals 2. So we would get 4, right? So we'd write d dx of, maybe we put like x squared here of 2. There's different ways to write it. Okay, so we would get 4. So the slope at this point is equal to 4, which happens to be the same as the output at this point, but it doesn't need to be, of course. So how do we extend that now into multiple variables? Because of course, if we're looking at a surface, then there's kind of two different ways that it can change. So if we have a function f of x y is equal to x squared plus y squared, okay, then this function is going to change, meaning the output of the function will have some kind of rate of change associated with changing the x value, but then it's also going to have some sort of rate of change associated with changing the y value. So there's kind of two different rates of change going on here, one for the x and one for the y. So with this in mind, we can define two different derivatives for each one, and we call these partial derivatives, because it's not telling us overall how much the function is changing. The partial derivative with respect to x would tell us how much is this function changing as x changes only. So in this context, we would be holding y constant and seeing how much x changes. Same thing with the partial derivative with respect to y. We would say, okay, how much is the output changing as y changes while holding x constant? Okay, So to make an analogy to statistics, if you've already done some statistics work in some classes, it might make more sense hearing it this way. Or if you think about a multiple regression, like a multiple linear regression, if you have two variables x1 and x2, say, then when you come up with your coefficients in the multiple regression, this is exactly the same idea that you're doing there, right? You are finding how much does one variable change as you hold the other one constant. And that's not a coincidence. It's actually, as we'll see, it actually is because, we can just look at the partial derivatives of those. But we'll, go ahead and look at how to take the partial derivatives and stuff like that first. So let's go ahead and just define the partial derivative. So this will look just like how the single variable version looks. So let f of x, y be a function of two variables. Okay, but again, as I've mentioned, you can extend this very naturally to 3 variables, 4 variables, whatever you need. Then the partial derivative with respect to x, and then there's two different ways to write it here. So written as either this with, it's like this D symbol with like a rounded top here. Okay. F. So we read this as partial f over partial x. Okay. Or we write it as f with a subscript of x. Okay. So this is obviously the easier way to write it. But I think this one's probably a little more common. Just in general, like, so this is the same as the Leibniz notation, just using a different symbol for the D here. So, I mean, you'll see both of these kind of often, but I think this one's probably a little more common in this context. So, so this is defined as, so we have partial f partial x is equal to the limit as h approaches 0 of f of x plus h comma y minus f of x comma y over h. Okay, so you can see we're basically just leaving y alone, right? So this is the idea of holding y constant. So y is just kind of coming along for the ride here. So you can do the same thing with y. I won't write the definition there because it's exactly the same. Just, put the y plus h in there instead. And as we remember with derivatives, evaluating them directly from the limit can be kind of tedious. So we have all these different rules to evaluate the limit, or the derivatives. And those will all pretty much hold the same with this idea of a partial derivative. So we'll still have the power rule, we'll still have the product rule, quotient rule, all of that. So the key thing is that if we're taking the derivative with respect to x, then we need to hold y constant, meaning we need to treat y as a constant, just like we would have treated like a number or something like that with ordinary differentiation. And same thing with y. If we're taking the derivative with respect to y, then we treat x as a constant. So if we wanted to take, so say, as an example, so we have this function f of xy equals x squared plus y squared. So if we want to take the derivative with respect to x, we might write it like this, first of all. So we take the derivative as we normally would. So by the power rule, the derivative of x squared is 2x. Now y is a constant here. So the derivative of a constant is going to be 0. So this will be 2x plus 0, so 2x. Okay. And then same idea for the partial derivative with respect to y. X here is a constant, so that's 0. The derivative of y squared would be 2y. So this will just be equal to 2y. Okay. One thing to note here is, often because we're using y here, some people will kind of get this a little mixed up with implicit differentiation, or maybe just not really see the difference. And the difference here is that in implicit differentiation, when we were taking the derivative of y was a function of x. So, it was a dependent variable. Here, x and y are both independent variables. Neither of them are functions. Z is a function of x and y. So if we were taking the derivative of z, then we might need to think about implicit differentiation. But in this case, x and y are both independent variables. They're not functions of each other or anything like that. So we don't need to worry about implicit differentiation here. So this is a different thing. So let's look at a bit of a more complicated example here. So let's say we have f of xy equals x squared minus 3xy plus 2y squared minus 4x plus 5y minus 12. Okay, so two different derivatives here. So if we take the partial derivative with respect to x, we'll use the Leibniz notation this time. So we'll just go down the line and use our normal derivative rules. So this is 2x. Here the y is a constant. So this is going to be minus 3y, right? Just like the derivative of like 2x would be 2, right? It's just the constant part in front of it. So here 3 is a constant, y is a constant. So they just come along for the ride. We use the power rule on x and that just becomes 1. So we get minus 3y. This one is 0 because it's a constant. This one is minus 4. This one is also 0. And this one is 0. Okay. So ultimately our derivative is 2x minus 3y minus 4. Our partial derivative with respect to x. Okay. So now the partial derivative with respect to y, we get 0. This will be minus 3x, because again, the x is treated as a constant. This one will be 4y. Then we have 0 plus 5 minus 0. Okay. So we have minus 3x plus 4y plus 5. Okay. So the process of taking the derivative is exactly the same. We just have to keep whatever variable or variables, if we have more than just two, whichever ones we're not taking the derivative with respect to will just remain constant. Okay. So I'll just do a couple more examples here. And then in the next video, we'll kind of look at some interpretations of the partial derivatives. We'll look at the visualizations of them. Okay. Here, why don't we, here's a couple of good ones here. Let's do f of xy equals x to the 8th, e to the 3y. Okay. So here we want to do the partial f x. So e to the 3y, the whole thing is going to be a constant, because this is just like e raised to a constant is how we're thinking of it right now. So it's just going to come along for the ride, essentially. And then we'll use the power rule on the rest of it. So this is 8x to the 7th, e to the 3y. Okay. And then same thing for the partial derivative with respect to y, except now we do have to invoke the chain rule a bit here. So x to the 8th is just going to come along for the ride. This is going to be e to the 3y times the derivative of 3y. And when we're talking about the derivative here, we're still talking about the derivative with respect to y. Okay. So this is just going to be 3. So in other words, 3 x to the 8th e to the 3y. So speaking of the chain rule, let's do one which involves the chain rule more prominently. So let's say we have z equals ln of x to the 6th plus y to the 4th. Okay, so sometimes we'll write z equals instead of f of x, y equals, just like sometimes we would write y equals instead of f of x equals for single variable functions. So partial of z with respect to x. So the chain rule here is going to give us 1 over the stuff inside the log times the derivative with respect to x of the stuff inside here. So 6x to the 5th plus 0. So in other words, this is 6x to the 5th over x to the 6th plus y to the 4th. And then the partial of z with respect to y, same idea. So we'll still use the chain rule and get the same thing at the beginning. But now this is going to be the derivative with respect to y of this stuff on the inside. So times 4y to the 3rd. Okay. And there we go. So that would be it.